Alright, today we're doing chapter 9 in the Barron's book. It is solutions, so get pumped. Alright, the first thing this unit does is mention some vocab, which we will be using. So, there is solution, obviously, and that is a uniform mixture of one or more solutes dissolved in solvents. So, remember, solvents dissolve, solutes are dissolved. So that's pretty big to know. Alright, well, the next word they have is alloy, which you probably know. It's just it's a solid solution of two or more metals. Pretty much just mixing metals together, usually through the application of heat and or pressure. So the next thing they have is quantitative, so like quantitative descriptions. This is kind of, you're just specifying like how much is in the solution. It is like it sounds like quantity. It's just numerical terms for the solution. So this is also usually associated with concentration, which we talked about last unit, which is big M. Molarity, right, which is moles per liter. This is concentration. The next word, solubility, just refers to the amount, usually in grams per liter, that a certain element or molecule can be dissolved in a certain solvent. So, like if I just have a solution that has a solubility of 2 grams per liter, that means 2 grams of it can be dissolved in a liter before it's a saturated solution, which means that if I just add more solutes or more of the element, it just won't dissolve. It'll just float around solidly in the water, or sink, as the case may be. So, final one on this first page is molar solubility. This is the maximum amount in moles per liter that a solute can dissolve. So I'm not writing all these down. They are in your book. They're also pretty easy to look up if you don't have a book. But again, not too bad. I'm just running through them pretty fast. I think you can handle reading on your own. Well, yeah. Well, next word is qualitative. Analysis, really, which is a non-numerical analysis. So yeah, that's pretty much what it is, non-numerical analysis. So next is dilute or diluted. This is just a small amount of solute and a large amount of solvent, meaning that it has a low concentration. So yeah, and as I mentioned earlier, saturated, that's the next word, saturated solutions. It means the maximum amount of a solute is dissolved in the solvent. An unsaturated solution, which you might be able to guess, is when less than the maximum amount is dissolved in a solution. So finally, you get one that's kind of a little weird. It's called supersaturated. This is when there's more than the normal amount. I'm going to put this one down too. So you're probably like, how can you have it greater than the maximum dissolved? Well, solubility depends on heat because it adds more space between the molecules. I'll get into the physics behind that later, probably in the next solution, the next section. But what you need to know is that a higher temperature will make a solute more soluble, which means it can more of it can be dissolved, and this if you heat up a solution, you can dissolve a bunch of solute, and then if you cool it down slowly, the solute will stay dissolved, and you will get a supersaturated solution where you kind of snuck in more than you actually can fit in in the solvent. So there you go. And the last one is metastable, which means that just that excess solution will crystallize. So that usually applies to supersaturated solutions, where if they are disturbed, like shaking them up, or if you add like a seed crystal, they're called, it'll start a crystallization process. So all the excess solute that you add to the solvent will undissolve and crystallize. So there you go. I know, a lot of vocab, but imperative that you know it. But I wouldn't worry too much about it because you should learn most of it through the next few slides and practice. So that's just basics. Alright, so this is a huge rule in solubility. This is a big one you need to know. Memorize it. That's kind of a scary word because it's only 3 words, so memorize seems a little extreme, but you need to know like dissolves like. I said it before in past videos, but this usually refers to polarity. So like water is a polar molecule, as we all know. It's probably, well, there, if I do that, you can probably see the dipole moment. But anyways, water's polar, so it's going to dissolve polar substances like ions. If I have salt, NaCl, well, Cl is going to be negative, Na positive, right? Ions and all that. What's going to happen is the positive side of Na is going to be attracted to the negative side of oxygen, whereas on the other side, the negative side of chlorine is going to be attracted to the positive side of H2O, and what's going to happen is they're just going to split right down the middle. So you get H2O. This process is called dissociation, usually when it's, and it is dissolving. It's also called dissociation because the ions are dissociating, or the molecule is dissociating to its ions. Then you have that, and you have that, where they're just attracted, and now you just have them free floating in the water. So this molecule is dissolved and is dissociated because it was ionic, and now it's split back into its ions. So like dissolve like, mostly through attraction. Same things happens for nonpolar solvents with nonpolar solutes. So remember, like dissolves like. Cannot stress that enough. Know it. Alright, so the book describes dissolving in 3 simple processes. The first step is that the solute, which we'll call this guy up here. Oh, that is hard to read because that's on the edge of the screen. Alright, that'll be the solute. This will be the solvent. What happens here is the solute is going to space out so that the solute is going to space out so the solvent can fit in between it. So it's spread out, right? Well, step 2 is at the same time the solvent is going to split out so the solute can fit between it. So now there's more space in between these molecules. Well, the final step is they just combine. They're just now in between each other. So these molecules, where they were separate before, they now have room to intermingle. There's space between them. So now you're going to get like solutes and then some solvents. Yay! So then that's the solution. So there you go. Just separating and then intermingling. Really seems kind of like 2 steps because 1 and 2 are happening at the same time. But there you go. Also, side note, if you were in the book with me on page 319, the book mentions entropy. Don't worry about that. It is a term used in thermodynamics, which is going to be a later chapter. And it's kind of hard to explain, and it's also kind of confusing. Really just not worth going into at this stage. But if you want to know what entropy is, or you need to at this moment, you can watch the thermodynamics video, I believe is when that unit is, or when entropy is covered. And I will go through it in detail then. So, yes, there you go. Moving on to the next section. Alright, so now the book is giving you examples of the solution process. The first one they show is an ionic compound. I already explained and showed that one. If you want to watch that one again, just rewind a little bit. I don't want to explain it again. There's not a real point because I already covered it, pretty good depth. But that was with the water dissolving the salt, or the NaCl. So the second example is the gas mixture. This is pretty simple. I mean, the book tries to explain it in terms of entropy. Again, don't worry about it. Useless right now, but I can draw you a picture of what's happening. If we have gas 1 is white, and it's just a bunch of, you know how gas is, particles, they're all flying around. And if I have gas 2 in red, well, luckily for us, gas does something pretty convenient when it mixes. It distributes perfectly evenly. Well, I shouldn't say perfectly even. It is random motion, but it doesn't separate itself. So gas is just around doing its thing, being nice and well mixed. So there you have it. That's gas mixing. Very easy. Because if you want to think about it like this, gas already has space between the molecules, so they don't need to split or separate like the solute and solvent did in the previous slide, and it expands to fill all available space. So when there's two gases, they're both going to expand to fill the available space, and they'll both be mixed. It's not like there's invisible walls separating them. So here you go. That's gas mixtures. Alright, the next thing covered is rates of dissolution. Luckily for us, there aren't any equations for us to know on this section. All it is just it's conceptual. So you just need to know what you can do to speed up the reaction, or in this case, the dissolution. So if you remember before, I have said that a chemical reaction, or in this case, dissolution, can be sped up by increasing surface area. With solids, the way to do this up is to grind up. To grind up the solid, turn it to powder, right? The powder will have much more surface area than a cube of the solid. I mean, it's not too hard to think of why, but that's just the truth of it. And the powder will then react, or in this case dissolve, much faster because there's more surface area exposed to the solvent. Alright, and as many of you can probably guess, the other step for speeding up this reaction is heat. Now, heat won't speed up all reactions, but all you need to know for right now is that heat speeds up dissolving, which goes hand in hand with the idea that heat also lets you dissolve more. So super saturate and speed. That's what heat gives you. I'll try to make that more legible. Super saturate is what that's supposed to say. Oh, that's awful. Let me fix that. 8. Super saturate and speed. So these are the two things that will speed up dissolution. So as you can probably guess, the way to slow it down would be to have lower surface area, so get a bigger solid, or less heat, so cool the substance. So that's all I need to know for now about rates of dissolution. Pretty simple. This will speed up. In case that was not clear, I'm pretty sure it was, but there you go. That's how you determine the rates of dissolution. So on the AP exam, you might get a question like, this reaction is happening at this rate, or maybe the salt is dissolving at this speed. If it's short answer, they might say, explain how we can make this happen faster. If it's multiple choice, you might just get several options, like 1 might be shake up the solution, 2 might be heat the solution, a third option might just be like cool the solution, and a fourth option might be add more salt, and you'd pick heat, right? Because that's the one we cover, that speeds it up. So, there you go. That's something you might expect on the AP exam, because it's conceptual and it's pretty easy. So, there will probably be one question like this for either dissolving or reactions in general, which we'll probably have to do with catalyst later, which I will cover later, but later is not now. So for now, that's rates of dissolution. If you remember at the start, I said you could, not the start of this video, probably like chapter 1 or chapter 2, sometimes you might have to write, like if this is your cation for sodium, this is sodium or Na+, you might write a Q in parentheses next to your atom or your ion in this case. Well, by now in chemistry, I hope you know the AQ stands for aqueous and what aqueous means. But if not, it is in the book right now, so I'm going to cover it again right now. This just means that this sodium ion was dissolved in water, and because it's dissolved in water, more than likely it was also dissociated in the water, so it's probably part of a nice little polar ion, so probably like NaCl or NaF or Na2S. Just a ton of things. You know how to make chemicals really, or write them out anyways. But there you have it. The water, remember from before, like dissolves like, the ions dissociate in the water, and anything dissolved in water will be an aqueous solution. So there you go. But these ions are important because when an ionic compound is dissociated, let's get a new color on this. Dissociated, I'll just put dis for now. Dissociated. It turns into something called electrolytes. You probably have heard of these before, probably in like Gatorade maybe, they have electrolytes in it. I don't know, I put that line at the end. But they turn to electrolytes. Electrolytes are just dissociated ions, and when ions in a solution and when an ionic compound is dissolved in a solution, its ions dissociate completely or a lot. It conducts electricity. You'll remember this as a physical property from the crystal unit. Also, that is also with melting, it conducts electricity, but in this case, we're talking about electrolytes and dissociation in water, or in any solvent at this point. But if they dissociate well and they conduct electricity well, they are strong electrolytes, or just electrolytes. If they don't dissociate very well, they are weak electrolytes, and they also won't conduct electricity very well. And if they don't dissociate at all and they do not conduct electricity, they are non-electrolytes. So strong electrolytes, again, this is about dissociation into ions, they tend to be pretty much all the ions, or all ionic compounds. I don't want to say all, because there's usually one or two exceptions to every rule ever, but in this case, it's going to be all or so close to all that it doesn't matter. You don't have to think about the not. So pretty much anything ionic. This is going to be like HF, NaCl. You know ions at this point. Make your own. So many ions. Alright, well, the weak ones that do not dissociate very well, these tend to be, if I switch colors, molecular. Missed a letter. Erase. Start that over. Molecular. So, if you remember from your crystals, they're pretty soft. They don't conduct electricity or heat very well. And these are going to be, molecular. They're going to be, just molecular. I mean, Mostly, when you're thinking molecular here, you're probably going to think organic chemistry. Again, you haven't had organic chemistry, but pretty much hydrocarbons are going to be a huge group of this. So you start seeing things like CH4, methane, and you might see some acids, like this one is called ethanoic acid. Again, don't worry at all about the names, you'll learn them later, but these ones, they don't dissolve well. Now, this is largely because they're not polar or not very polar. So this means that when they're dissolved in water, for example, which is a nice polar solvent, they won't dissolve very well at all, and they'll be weak electrolytes, and that means they do not conduct electricity. So, there you go. No electricity, don't dissolve well, not very polar. There's these guys. They're polar, and they do conduct electricity. So, that's strong electrolytes versus weak electrolytes. So, non-electrolytes are, I guess I should write this too. There are molecular compounds that dissolve but tend to not dissociate into ions. I guess we're only going to talk about the soluble ones because those are the only ones that are really relevant, but these are going to make no dissociation, so they're not going to conduct electricity at all, whereas the weak conduct it a little bit. So this could be no E. And these are going to just be probably a lot more hydrocarbons, so like glucose, so a lot of sugars, like glucose, C6H12O6, if I remember correctly, I think so. So I'm just going to put sugars down here, so remember that, and then alcohols. Alcohols are very soluble because they have an OH group, which makes them pretty polar. And they are, again, molecular, but they do not create electrolytes, hardly at all. So they are non-electrolytes, actually. So alcohols, like pretty much anytime you see a hydrocarbon with an OH at the end, like CH3OH, that's methanol, C2H7OH, that's ethanol. So anytime you see this OH means alcohol. That's all I'm going to go into for the vocab naming right now, but that means it is a non-electrolyte in this case. There you go. Alright, so the next section is going to cover just a bunch of concentration terms. I'm probably just going to list them out. Their uses aren't too difficult. I'll probably just explain them as I go. But first one, molarity. You all should know by now. Symbol M. And this is mole solute over liter solution. So as liter or moles per liter, if you remember from before. That's pretty much what it means in terms of solutes and solvents and solutions. Big M, you can use this to, this is just the concentration, right? So we're going to use it a lot, especially in acids and bases. The next thing, not to be confused with molarity, though it easily could be, is molality. This is a little m. This is mole solute over kilogram solvent. It seems kind of weird, but if you're given an equation where you get the mass of the solvent and you know the molality, you can solve for the mole of the solute, and then once you have the mole of the solute, you can do all sorts of fancy things, like maybe solve back for molarity. anyways, I'm sure we'll do some example problems in the book in a minute when they go over all the sorts of calculations you can do, but that's all you get for now. Next is mole fraction. It's represented by that fancy, like that guy. It's a fancy X pretty much, and this is mole solute again over total moles. So you can see how that's pretty related to molarity, right? I should use a different color for that one, my bad. I'll switch on the next one. But view the mole fraction, the molarity, you could probably do some serious damage stoichiometry wise. Might be able to figure out and like maybe solve for what solvent you have based on its mass and its amount of moles, what you would get from the mole fraction and the molarity, and then that would let you analyze what elements or what molecules the solvent is made up of. Next one, mole percent. This goes hand in hand with the mole fraction. Is just 100 times that, and that's all it is. So this one doesn't even have a symbol. Just pretty easy. Alright, next we have something called the mass fraction, and this is WT over WT. I assume that's supposed to be like weight over weight. Don't ever confuse mass with weight. So it's going to be mass solute over mass solution. Now, in this case, it doesn't like ask you to use kilograms like the other one did, especially because they'll just cancel out. So just make sure you use the same unit for both of these, right? If you have kilograms on top, you want kilograms on bottom, and so forth. The mass percent, much like the mole percent, is related to the mole fraction. The mass percent, or the mass percent is greatly related to the mass fraction. All you do is find that fraction and then times it by 100%. So next we have something called parts per million. Some of you who have done maybe like apes have heard of it. They usually use it to like find the concentration of toxins or pH in water, because water is the habitat for many living things, and changes in acid content could, even slight changes, can be horrible. I'm not sure why I put that line there. They are very related, obviously, so that's maybe what I was thinking, but they do have their own signs and what they are. So parts per million is just the mass percent, or the mass fraction, so WT over WT, and this is times 10 to the 6th. So you know your powers. 10 to the 6th is a million, hence part per million. As you probably guess, this one's WT over WT times 10 to the 9th. So this is good for dealing with low concentrations. That's pretty much it. That's all the concentration terms you will be needing for this chapter. I know it seems like a lot, but to be honest, on the AP test, never used that one, never used that one, never used that one, never used that one, never used that one. I don't even think I used that one. And this one, rarely, so I'll just give it a check. But the big ones, you should know all of them because the book has all of them. And your teachers, I'm sure, will want you to know all, if not most. But this one, those are the two huge and most commonly used ones. So there you have it. That is concentration terms. But again, you can use all of them in math. They're not too hard to plug in. Obviously, it's just plugging in data and solving. But you probably only need to know molarity and molality. The other ones I would know, but it is a lot of work to memorize things like that. And it's most of them, if any, I lost that train of thought. Most of them will not be on your AP test, and I doubt any of them at all would actually be on your AP test. I did not see any of those. Ick. I will just do an example of the most commonly used one, which is molarity. So the problem in your book is a solution prepared by dissolving 25 grams of magnesium chloride in enough water to make a 450 ml of solution. So calculate the molarity of the solute. The first thing you're going to do, right, for molarity, for this, you want to know how many moles, right? So the first thing you're going to do, as you all know, stoichiometry, you're going to turn your 25, if I could write, 25 grams over x mole equals, well, you can solve for the math on your own, but I did it already, which is, it has a molar mass of 95.21 grams per mole. Mole, you calculate it out, times each side by x, and multiply by 95.21, gives you 25 over 95.21 equals x mole, which equals 263 mole MgCl2. Now it's pretty important to label what chemical you're finding the mole of, because later you might be dealing with several chemicals and you might get mixed up on what is the amount of which. So the next thing you're going to do is, well, it said the amount of water is added to enough water to make 450 ml solution, or milliliters, ml. So now this is pretty important, so I'm glad they brought it up, is for all of this, I'm going to say, assume the volume of solute is 0 unless told otherwise. This is a good rule because as things dissolve, they usually, like, for example, the small amount of MgCl2 or magnesium chloride that this is going to be, volume-wise, going to be tiny compared to the amount of water. Just makes it almost negligible. Also, it is hard to solve for the volume of the magnesium chloride unless it's a regular shape, or they tell you the dimensions of it and it's a regular shape. Or if they, well, another thing that might happen is they might, like, explain an experiment where displacement happens, like where they give you volume 1 of a thing of water, and then, now this is not related to the problem right now, I'm just showing you what might be on the test. Volume 2 of the water after the solute is added, which would show you the increase in volume, which would tell you the volume of the solute, but in this case you'd already have the final volume just from looking at it. So again, big rule. In this equation, it does not tell us that there is a volume for this much magnesium chloride that is relevant or not negligible, so we're just going to continue solving like nothing happened. Take our 0.263 mole over, now remember, we had 450 liters, right? Well, or 450 milliliters, I'm sorry. Well, molarity, remember, big M, equals moles per liter. We can't put 0.263 over 450 because that's not right. That's not how many liters there are. So we need to convert that into liters. You know your roots by now. You should know that 1,000 milliliters in 1 liter, which will give us 0.450 liters on the bottom. That's going to be M, which gives us a final answer of 0.584 M, or 0.584 moles per liter, which, again, visualizing this, that means if you have if you had 1 liter of solution, there would be 0.584 moles of magnesium chloride in it. So there you go. That's an example. Again, molarity is the most common, if not the only, one of the previous concentration things that you need to know, at least in my personal AP experience. So this is the only one I'm going to do an example for, because the other ones are rare and similarly easy to do. They'll give you enough data to solve for it, and you just set up the equation with the data and solve for the missing value.